Welcome to our next video in the series on condensed matter theory. In this video I want to talk about an example of a tight binding model, and we look at the tight binding model for the alkali metals. So in the periodic table, going from lithium to potassium to francium. The left row in the periodic table, the left column in the periodic table. The alkali metals can be described as free electron-like. You have a noble gas configuration plus one extra electron, which in the atom sits in the S shell. So we can start to make a tight binding model with an S band only. And as we have seen, for S bands you can't make a completely free electron-like model. But when we include both the S and the p orbital, we should be able to get free electron-like descriptions of these materials. So if we look at a free electron-like dispersion, then it should be a quadratic dispersion. Energy is proportional to k squared over 2m or p squared over 2m. And then of course at the zone boundaries you get a folding of the bands, such that you get for a one-dimensional square or a one-dimensional chain these nice kind of bands that we have seen before. Now the Brillouin zone is not one-dimensional, but we have a three-dimensional system, and it's not a simple cubic, but it's body-centered cubic. So inside the cube there is another atom, which leads to a Brillouin zone which has this beautiful shape. And we're going to make a path through the Brillouin zone in the 1, direction, which moves from gamma to p. And then we continue, we don't get back to gamma, but you go via h, which is the x, y, or z direction in the Brillouin zone, but then of the neighboring Brillouin zone. And then you get back to gamma from there. So in red, we see the band structure as we calculate from density functional theory. In this case, not with a comparison to the experiment, but with the comparison with experiment is reasonably good. There are no very high quality experimental data that I'm aware of, but if you look at the older data, then the points where they have measurements, they agree. And in thick blue, we see the free electron-like dispersion with the mass of the electron. And you see that indeed the bottom of the bands, as well as at the Fermi energy sitting here, you have a reasonable free electron-like dispersion with a slightly reduced mass. Sodium, potassium, rubidium, cesium, francium. And we see that the real space lattice constant increase when we go down in the periodic table. So the reciprocal lattice constant decrease when you go down in the periodic table. And that's exactly the scale that we have used there, such that the free electron-like dispersion just stays the same. Now if you look at the atomic orbitals, I plotted them here, the 2s for lithium, then you see that the atomic orbital is non-zero at the site of the neighbor. You also see it's a 2s, so we have one node. The 1s would go immediately here. And we can or have to repair this in order to make it a good basis function. And the basis functions that we are talking about are then confined in the region up to the first atom. Now, the functions that I show here are still not orthogonal, but for a basis that is still okay. And it is this basis that you work on internally. So how can we make tight binding like wave functions starting from free electron-like states? So if you look at the free electron wave function, then at gamma it's e to the I kx or kr, k is 0, so it's just going to be a constant. At the zone boundary, e to the I kx, at k is pi over a, you have exactly a change of phase with a lattice constant. So the phase is plus minus, depending on where you are in the real space. Then at the next gamma point, the phase is 2 pi, such that the phase at the atom sites is always positive, and you have a change of phase in between them. So the higher you go in energy, the shorter the wavelength becomes. And of course this point is folded back to gamma, instead of sitting at 2 pi over A. Now if we look at the wave function that you get if you just add the atomic wave functions with the same phase on each side, then in between the atoms this becomes a reasonable constant. You have these two exponentially decaying functions. If you add them, they turn out to be reasonable constant in between. At the nucleus we of course have this additional node because it's a 2s instead of a 1s orbital. If you look at the density, then everything becomes of the same phase, and you see that this is roughly a constant density as you would have for the free electron state. At the x point we have the atomic wave functions with phase plus, minus, plus, minus. So if we add the atomic wave functions with alternating phase, then you see that you get roughly a sine-like wave function, again with this additional node. If we change the sign of that node, then you see that you have a reasonable sine-like wave function in there. Now what do we do at the next point in the Brillouin zone? Gamma. And if you want to make a tight binding model with a single s orbital, then you only have one state per unit cell, so you have only one band in your Brillouin zone, and you cannot even represent this. So in order to represent this, we have to add another state to our basis. Well, we want to have a state with an additional node, so instead of a 2s we could look at a 3s. However, if we shift the phase of our wave function, then we see that the node can also sit at the atom side instead of in between. And at this point it's a wave function that is odd, and we can take the 2p wave function, which is just lower in energy than the 3s. So if we take the 2p wave function and we add them with the same phase on each side, the phase here and there is the same, then this is what we get, and you indeed see that you get the sine-like wave function with higher phase. It's a bit skewed because you have this additional core potential in there, but otherwise close enough to be a free electron-like sine wave function with higher periodicity. So if you move in the x direction, you have an s band here and an px orbital there. If you move in the y direction, you would have a py orbital there, and if you move in the z direction, you have a pz orbital in the next Brillouin zone. And that's actually a beautiful coincidence. We have 3 p orbitals, we have 3 directions in which we can move, so that we fully use our basis set of p orbitals. The s orbital at gamma, and the px, py, and pz orbital at the next point in the nearest neighbor Brillouin zone for gamma. So gamma 2 is made out of px, py, and pz. Very well, so this works in terms of basis sets. Now let's see what happens when we make a tight binding model for the lithium orbitals that I showed with an s and a p orbital, including nearest neighbor interaction only. And in green I show the s character, and in blue we have the p character of our bands. And you see that indeed the quadratic-like dispersion can perfectly be reproduced on such a basis set of having only s and p orbitals in our basis and nearest neighbor hopping. And of course, when you go to the higher bands, there are some deviations, but it's not even so bad. And if you go even higher, then of course there are more bands that are missing. These are the next orbitals in our basis set. We only have the 2p and 2s in our basis set. We have also the 3s, 3p, 3d orbitals that are just missing and that are needed to represent the atomic or the full Hamiltonian at higher energies. So we can also have a look now at how these wave functions look like, and you see that the p Warnier orbital is reasonably atomic-like. The s orbital is, well, slightly deformed from a sphere, but it's all within reasonable agreement as you could expect for them. And it definitely has all the symmetries that you should expect in that orbital. Now, instead of lithium, you can look at sodium or potassium or rubidium. And what you see here is that the wave functions don't change all that much. Of course, my units change because the box size, the way I draw them, has been made the same. My wave functions get bigger and bigger when I go down in the periodic table. Therefore, the brilliant zone becomes smaller and smaller. But of course, I can just take as a scale here the distance between two atoms. And you see this all works very nicely for all of the states that we have going from lithium to rubidium. Well, you see that you get more and more internal nodes in your orbitals when you go down and down, because lithium is 2p, no node, 3p, 4p, 5p, 6p, etc. So this way we can make a tight binding model for free electron-like bands. And we also see that well, the number of additional bands that you get that are not represented in our basis is getting larger and larger. When you go deeper in the periodic table, the heavier the atom, the closer the principal quantum numbers get to each other. So the lower the energy of the excited states is. Or in terms of free electrons, the heavier the atom, the bigger the unit cell in real space, the smaller the unit cell in reciprocal space, and therefore the more folding of your bands you get. We now can also understand why a free electron-like model works for sp bands, but not for d bands. And that is coming back to this picture. If I want to make a free electron-like band, I have to mix an s and a p orbital. And this I can do when I go from gamma to the neighboring brilliant zones, and there are exactly 3 of them. So this allows me to mix in px, py, and pz. If you want to do this with d orbitals, then you'll notice that you have 5 d orbitals, but we only have 3 dimensions in our space. So there are always 2 orbitals left in some sense. It just doesn't fit. And the reason that we can neglect Coulomb repulsion is not so much that the interaction is small, but much more that there is no phase space to which you can scatter. If all states up to the Fermi energy are filled, then you can only scatter electrons from below the Fermi energy to above the Fermi energy, and there's always a gap or an amount of energy associated with this, unless you're perfectly at the Fermi surface, but that's only a very small amount of electrons compared to the total number of electrons. When you have d orbitals, then there are always 2 orbitals at the same energy that are available. So this idea that you fill up the entire phase space and therefore you have no Coulomb scattering is no longer valid. So there is always some possibility to do Coulomb scattering, and well, when it breaks down, it starts to break down hard, because we do make we make an approximation where we neglect the large part of the Hamiltonian instead of the small part of the Hamiltonian. So this idea of we have a Fermi surface that is filled, we can therefore neglect Coulomb scattering because there is no phase space, and we can optimize both the atomic wave functions as well as the kinetic energy in a solid, works for sp-like materials, but no longer when you have an open d or f shell. And well, then it gets really interesting, but that is really for next year's lecture. Before we are able to dive into that, I want to talk about Green's functions, which is what we will do in the next set of lectures. And then we have the tools with which we also can dive into through interacting many-body physics. For now, I want to leave you with the beautiful tight binding representation of free electron-like bands as you encounter them in real materials. In the next few videos I'm going to do an example of MgO and nickel oxide, two insulators, just to see how well you can understand the tight binding and the band character partial densities of states. And then I hope you have a reasonable idea how electronic structures in different real materials work. Thank you very much for your attention. We see each other in the next video, and stay healthy.